recall. All right, recall that complex power S we said was capital P plus JQ. Real part plus imaginary part. Average real power plus the imaginary part, which is just the reactive power. Now, we're going to substitute in for P and Q. So here's P and here's Q. We know what those quantities are as they relate to the sinusoid. So we're just going to substitute them in there. And where we're going is I'm going to show you that S, the complex power S, is a phasor quantity. And I've been kind of hinting that all along, but we're actually going to do it now. So when we substitute in, we will say that S is equal to, for P, remember the equation for P that we used a few lessons ago was the following. It's Vm Im over 2 times the cosine of theta V minus theta I. Okay, that is P. So this is basically exactly from a previous lesson. This is how you calculate the number P, the average real power. Plus, we're going to add to that, with a J there, we're going to put in what we know Q is equal to Vm Im. This is why we spent time before solving a few problems, just a couple of problems, finding P and Q manually. Sine of theta V minus theta I. All right, so this is essentially the complex power S. This is P, and this is Q, and this is all stuff from previous lessons. We're just kind of tying it all together. Now let's do a little bit of simplification. You see we have this term here, which is exactly the same as this term here. So we're going to factor those guys out and see where we go. S is equal to Vm Im over 2, and we'll open up a pair of brackets, and inside we'll have cosine theta V minus theta I. We'll have parentheses around that, plus J times the sine of theta V minus theta I. And we'll close the brackets off. Okay, so where we're trying to go here is to show you that this is basically a phasor. Now, here you have the very famous relation. Cosine of an angle, remember this is a difference of two angles, but effectively it's just an angle here, plus J times the sine of an angle. And if you remember, I'll put a recall off to the side here. Recall, this will be like a little aside here. The famous identity, e to the j angle is equal to cosine of the angle plus j times the sine of the angle. This is Euler's identity, and you probably haven't looked at this recently in circuit analysis, but if you go back to when I first introduced the concept of a phasor, this was actually critically important to defining what a phasor is. Because basically anytime you see cosine of something plus j times the sine of something, you can write it as a complex exponential like this. These are equivalent forms of exactly the same thing. You don't have to prove this. This is given to you by a famous mathematician named Euler a long, long time ago. But we can use that fact and stick it into here as follows, because now we can rewrite this and we can say that S, the complex power S, is equal to Vm times Im. These are the amplitudes of the voltage and the current. Divide by 2, but instead of this enormous thing in brackets, we'll just write it as a complex exponential, e to the j theta v minus theta I. Now what does that look like to you? Well, this is just a number. This is a number times a number divided by a number. So what we have out here is an amplitude, right? And here we have e to the j and then a number. And if you go back and look at when we introduced the concept of a phasor, this is a phasor quantity. When you have an amplitude, e to the j, with some number there, you can, that is what we've been using all along as the concept of what a phasor really is. So what we have done by knowing what P and Q is and by substituting in and doing a little bit of rearranging, we can write that S looks like this. But notice that when we've been working with phasors this whole time, we don't write e to the j angle over and over and over again when we write voltages and currents and things like that. We don't carry the complex exponential out because we'd be writing it 50 million times. What we do instead is we write it like this. So this is how we're going to formulate it. 1/2 Vm Im, and then we just write this angle bracket and we write the phase angle, theta V minus theta I, right? This is complex power. Take a minute to absorb what we basically said here. What we're basically saying here is we have this concept called complex power. If you can write it in algebraic form, real plus imaginary part, then you can immediately read the real power and the reactive power off, which is generally what you're always trying to calculate. So the question is, how do you find them? Well, you could go calculate cosines and sines and all of that stuff. Sure you could. You can go calculate P with this, and you could calculate Q with this. That's what we've been doing all along, but we want to show you alternative ways that might be easier, right? So another way to do it would be to use this concept of a phasor, right? And so what you could do is then calculate the amplitude of the phasor. You know the amplitude of the voltage, the amplitude of the current that you have, multiplied by a half, that's the amplitude of the phasor in polar form. The phase angle is simply just going to be theta v minus theta I. You stick that in your calculator. This is a polar form of a complex number, magnitude and phase of the complex power. And then if you hit your button on your calculator to convert this to algebraic form, or you can go manually and use the triangle to convert it to algebraic form, you'll just get P plus JQ back. So now we're going to take it one step further, and we're going to recast this equation, which we've already written down as the phasor of the complex power, and we're going to recast it in terms of if you're given RMS values, because a lot of times in AC you're going to be given the voltage and current in terms of RMS values. So, or in RMS values, then you can recast S as the following: V RMS times I RMS, these are the RMS values, times an angle, same angle, theta V minus theta I. Okay, and this is if basically if you're given it in terms of RMS values. Now I'm going to circle this whole thing, and we're going to talk about this stuff for a few minutes because it's really, really important. All right, this is one of the punchlines of this lesson. It's not the most important punchline, but it's really important. All right, so basically, first of all, when we're using this formulation, the Vm, Im, these are the magnitude, the amplitudes of the voltage and the current. But many times you're going to be given RMS value, so you use the RMS value times the RMS value of the current, and then you have a phase angle here. That's the difference is written there. But we drop the 1/2. Why did we drop the 1/2? It's because to go from Vm to VRMS, you divide by the square root of 2. To go from Im to IRMS, you also divide it by the square root of 2. So if you divide both of these by the square root of 2, then what you're going to get is a square root of 4, which is 2, which is going to cancel with the 1/2. So basically, you're going to drop the 1/2 when you get down there, and that's why it falls away. It's not an accident. So what does this mean? Okay, what this means is that, remember back when we were solving mesh current problems and node voltage problems, and when we're always finding the voltage and current across different components. Like the problem might say, what's the voltage across this inductor and the current through the inductor? And you would find a phasor, which would be the voltage across that inductor and the current across that through that inductor. All right. Well, what if now the third part of the problem says find the average real power? Okay, or what is the reactive power going through that inductor? Well, instead of going through all the theory and doing all of these things up here, all you would have to do is the voltage phasor magnitude, and the voltage or the phase angle of that voltage, right? Because you've calculated it with node voltage or whatever. And then you also know the current through the inductor, and you know its phase angle. So then all you would have to do is multiply the magnitudes, multiply by 1/2, and then the new phase angle of the new phasor is going to be the difference of these two guys. You just subtract them, you make that a new phase angle, and then boom, you have a polar version of complex power. Hit the button in your calculator or manually translate it into rectangular form, and then you can just immediately read P plus JQ, and you would know the reactive power just by reading it off. Just by formulating this new phasor and dumping it in, you can read P and JQ super simply, right? If you're given RMS values for the voltage and RMS values for the current, you just use this guy. It's exactly the same thing, but you don't use the 1/2 in front. So that's why I'm giving you two versions of the guy here. Very, 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 very useful. So let me now shift the page up a little bit, and we're going to talk a little bit more, I should say we're going to go a little bit further, which is going to be really interesting. Now let's take this a little bit further. What if we have S is equal to, we're going to be using this first equation up here at the top and going a little bit farther with it. So we'll have 1/2 Vm Im, and if you really think about it, this phase angle is representing this complex exponential, right? E to the j, and I'll just open it up here, theta v minus theta I. This is really the full glory of the phasor notation, right? We just shorten it by writing this bracket and sticking the angle in there, but this is basically the same thing as what we have here. So we can simplify that and say 1/2 Vm Im. Now what I'm going to do is, this is an exponential just like any exponential. I can split that up so that it'll be e to the j theta v minus j theta I. All I did is I distributed the j in, and I kept it, all of this stuff is still in the exponential up here. And then I can take this a step further, and I can say this is 1/2 Vm Im e to the j theta v times e to the negative j theta I. Now this is where you need to pay attention. All I've done now is this is e raised to a power of this minus this, which I can just split up into two different things, because when you have any exponent and you have something up top here, if it's the same base, you can just add them together. So all I've done is gone in reverse. I've split it apart. Notice if you add these guys together, you get exactly what you had in the previous step. So why am I doing all this stuff? Because if you really look at it, let me reformulate it, rewrite it down here below. S is equal to, I'm going to write the 1/2 out here, okay? And then I'm going to write Vm e to the j theta v. I'm just going to group the voltage terms together, times Im e to the negative j theta I. Okay, so you see what I've done. All I've done is I've taken this voltage, I've grouped it with this term that deals with theta v, and I've written it right there. And then I've taken this current magnitude, and I've grouped it with the term that involves the current phase, and I've grouped it right there, and the 1/2 just comes along for the ride. Why did we do all this stuff? Here's the punchline. Okay, this quantity is the phasor V. In other words, that's the voltage phasor. And this guy, notice there's a negative sign up here. There's a negative sign up here, so this is not quite the phasor, but it's really close. This is the conjugate of phasor I. And we call that the conjugate in terms of complex numbers is I with an asterisk, right? So let me finish the punchline here, and then you'll see how I'll kind of review it all, and you'll see why it's useful. This is 1/2 times the voltage phasor going through whatever circuit component you have, times the conjugate of the current phasor going through whatever circuit component you have. So we'll continue writing everything down below and formulate kind of the punchline right down here. So this means complex power is equal to 1/2 times the phasor V times the conjugate of the phasor I. Okay? And that's going to give you a phasor, and that's going to be equal to P plus JQ, which is what we talked about in the beginning. Now, if you're given in terms of RMS, in other words, if your problem involves RMS quantities, then you would calculate, you would drop the 1/2 is all you have to do because of what I talked about earlier. Because each of these V's and I's are going to be divided by the square root of 2, so you would you would drop the 1/2, and so then it would be the same thing, P plus JQ. All right, so let me circle this. This is actually even more important than the previous thing, but things can happen sometimes where you might have different ways of calculating the same thing. So why is this useful? Because don't forget, eventually we're going to be given a circuit, in the next problem. I'm going to give you a circuit. I'm going to say, find the complex power across this element. Or I might say, find the average real power across this resistor, right? So you can dig back through all the notes and find the formula for P and Q and try to calculate all these things manually. But this makes it incredibly simple. All it's saying is, you solve the circuit, you find the voltage and the current going through that resistor. The voltage and the current going through that resistor, and you're going to be doing it in terms of phasor. So you'll know the phasor voltage V as a complex number, and you'll know the phasor current as a complex number. So literally what this is telling you is, you take 1/2, you multiply by the phasor V, which is a complex number, and then you have to take the current I and find its conjugate, right? And I'll show you how to do that in just a second. Then you multiply these quantities together, boom, you have S. You have P plus JQ. You just read it right off your calculator screen. Then you would say, all right, well, the average real power going through this component is 15 watts, and the reactive power is, negative 24 VARs. And that's what you would read off. If you were given RMS quantities in your problem, maybe the source voltage was given to you in terms of RMS value of its magnitude, then everything you calculate, the phasors that you calculate through the circuit are all going to be RMS values. So then you would just, let's say you had a capacitor sitting across on the other side of the circuit, you would just take its phasor voltage, which is a complex number, times the current going through there, which is it's a complex number, but you have to take the conjugate of it, and you multiply those guys, and you immediately get P plus JQ. Now let's talk about for a second, what does this conjugate mean? Right? All it means is you put a negative sign in front of anything that has a complex number, right? When you have, in terms of rectangular notation, if you have 3 plus J4, then if you want to find its conjugate, then all you do is you say 3 minus J4. right? You just put a negative sign in front of anywhere you see a j. And that applies for the complex exponentials too. Let's say you have 3e to the j2, right, which is a phasor, right? Then to find its conjugate, and just say I'm going to calculate this guy's conjugate, it would be 3e to the negative j2. So finding conjugates is very simple. All you do is you put a negative sign in the appropriate place, and then boom, you have the conjugate. So finding this conjugate is no big deal at all. You just simply just put a negative sign in the proper place. You would put it in terms of the area where the phase angle is, and we'll talk about that a little bit as we do some problems, but basically finding this is no big deal. Notice what you have found here. Remember the very famous formula that we used way back in the beginning. How do you find the power across a resistor? I times V, right? That's the famous one, right? You just find the current multiplied by the voltage, boom, you have the power in watts. Notice this is telling me the same thing. The complex power across any element, whether it's a capacitor, an inductor, or a resistor, is V times I conjugate. So you just have to stick a negative sign in the appropriate place in the current phasor. You multiply them. That gives you the enchilada, the whole enchilada complex power, which you can then read the real part and get the average real power. And the imaginary part, which gives you the reactive power, you just read it right off of the screen there, and then you're basically done. So this is very, very similar to everything that we've done before. So let's go move up just a little bit. I want to close here by just giving you one piece of advice I want you to kind of keep in the back of your mind and keep aware of, okay, is that when we were doing this, we're going to use the same sign convention that we always have been doing. So assume the same passive sign convention. Which is very easy to understand. And if you remember back, if you have a circuit box, circuit element with something inside of it, and you have two terminals coming out, right? And let's say this one is the current, and then you have plus minus V. This is how we're going to write the sign convention. In this case, when we have the current going through a voltage drop like that, you write it with a positive sign. In other words, when I say you write it, I'm talking about the complex power here that you're calculating. You're just going to write it as V times I because the current is going in the direction of a voltage drop. This is the same as resistors or any kind of circuit element in basic circuit analysis. When the current was going through a drop like this, you write it with a positive sign in terms of the power. But if it's reversed, if the current's going down here through a voltage rise, like from a source, like if the current's going up and out through a source, then you would write with a negative sign. Right? So you have to keep track of that when you're calculating your power. If it's going through a rise, you'll have to stick a negative sign out in front of here, just like you do when you're dealing with regular power calculations before. So this is the lesson here. I'm going to take, because it's such an important lesson, let me go back to the beginning, and then we're going to just summarize everything really quickly, and then in the next section we're going to get down and dirty with solving some real problems. So what we have here is the idea of complex power. It's average real power plus the imaginary reactive power here. And then what we did is we said, all right, we're going to substitute in for P and Q. These equations just come from earlier. We're just going to substitute P and Q as we factor out these numbers, and then inside we're left with cosine of an angle plus J times the sine of an angle, which is exactly Euler's identity. So we're going to replace all this stuff with this complex exponential. This looks an awful lot like a phasor, and it is a phasor. So we can then say that the complex power is 1/2 V amplitude times I amplitude. The phase angle will be the difference between the two. All right? So, and then in terms of RMS values, you're given this guy here. Now we take it a step further, and then we say, all right, let's break this up a little bit more and see how far we can take this. So we start with this. That gives us this stuff here. This phase angle notation means e to the j and the difference of these phase angles. That's what a phasor is. So then we split it apart and we write it as two separate exponentials because I'm going to rearrange terms. I'm going to put the voltage with the voltage part right here, and I'm going to put the current with the current part, which is right here. And then you immediately look at this and you say, well, this is a number. This is just the phasor voltage through whatever circuit element I have. This is the phasor current, but it's the conjugate of the phasor current through whatever circuit element that I have. So then it allows me to write these really neat relations down here, which are really, really important, and that says that the complex power is 1/2 VI conjugate. That is if you're dealing with amplitudes. If you have the voltage amplitude and the current amplitude as a phasor, then you can just read P and J, or P and Q directly off of that once you convert to rectangular. If you have RMS values, you drop the 1/2, but it's the same thing. The important thing to realize is that this equation here, it looks like P is equal to IV, or very similar to it from DC analysis. But this equation here applies to any circuit element that you would have with AC current and voltage going across it. So if you had a capacitor or an inductor or a resistor or any giant network that consists of all three of them, if you know the voltage, the phasor voltage across that element, and you know the phasor current, take the conjugate, multiply it, then you're going to get the real and imaginary part. If you happen to be talking about the resistor, about a resistive element, just a purely resistive element, then what you're going to find is you're not going to see any imaginary part. It's just going to be purely real. So all of that stuff is going to be taken care of whenever you actually solve the problems. Whenever you get down to it, you'll find out that everything's taken care of without you having to think about things. You just read the real and imaginary part directly off of it. Now I'm going to close by saying one final thing. I've given you lots of different ways of calculating S. Ultimately, in a lot of problems, all you want to do is you want to find S because you want to figure out what the real power and the reactive power is. And now there's lots of different ways for you to do it. So don't get locked into one way. It's going to depend upon the problem you have as to how you handle it, okay? If I am given the voltage and the current amplitudes and their phase angles, I can formulate a phasor like this where I subtract the phase angles and I calculate a phasor and I'm going to get the quantity like that. Now sometimes things might be given to you that this is actually easier to do, okay? But in most cases it's going to be easier for you to come down here and just, you're going to know the voltage and the current through something, and you're going to multiply this times the conjugate of I, and you'll find that'll be the complex power S. And in other cases, you'll use that triangle that I showed you in the last section. You will use that triangle that we talked about, because that's functional and very easy sometimes to use as well. So I think that about does it for now. I hope that you've gotten something out of this. Basically, we can use these equations and relations. This is the most important one. If you know the voltage and current, having the complex power done for you is so easy to use. You'll see the power of it when we get to the problems here in the next section. I hope that you've had that aha moment. And if you haven't had it, I would encourage you to watch this a few times, because I've told you everything to try to connect the dots, but sometimes it takes more than one time to see something to realize the usefulness of it. So go back and take a look at that now. Follow me on to the next lesson. We will start to solve some problems, and you will see how easy it is to use these guys in circuit analysis.
Learn anything at mathandscience.com.